guys, we're still in chapter 15. This will be part 2. So hopefully you got good with the writing the equilibrium or expressions and manipulating K, so the equilibrium constant. And now we're going to talk about calculating them. And speaking of that, you will need a calculator. Let me go get mine. Sorry about that, y'all. I am back. Okay, just testing my pen. So remember I told you that it's an equilibrium constant, so it's going to stay the same as long as the temperature stays the same, and it's only occasionally that we change the temperature. So for the most part, K stays the same, and again, this is capital K, not small k from kinetics. All right, so what we do, we've got numbers at initial values, we've got numbers at equilibrium values, and we need to find K. So the first thing you're always going to do in a equilibrium problem is write the equilibrium expression. You have to do that first, okay? Because otherwise, how are you going to plug numbers in? Also remember, these are equilibrium expressions, and notice they gave us 2 initial values. So these are not equilibrium values. So I am going to make an ICE table. I'm going to explain what that is in a minute. Okay. The I stands for initial, C stands for change, and E stands for equilibrium. Okay, so the first thing we're going to do is plug in the initial values that it gave us. So it gave us 0.5 and it gave us 1. It gave us nothing for methanol, which is good because that means we're not starting with any methanol. Notice it also gave us the equilibrium concentration of CO. Okay, we do know that this specific reaction is going to proceed in the forward direction, and that's because there's no methanol. So the only way this one can go is towards the methanol. Okay, I know that seems a little weird. So methanol is going to change in the positive direction, and we're going to call that plus X, which means the reactants are going to decrease that same amount according to their coefficients. Okay, so this is 1 minus 2x. C is for change. And what you normally do is add the 2 I and C together to get the equilibrium value. I do want you to note, because it gave us this value on the bottom, I can say that 0.5 minus x equals 0.15. So then I can calculate x is 0.35. So once I've got x, I plug it in for the rest. So 1 minus 2x will be 0.3, and x will be 0.35. If y'all have questions, please ask, but we're going to do this over and over and over again, okay? So once I have true values that do not have x, all we do is plug them in. So I've got k is equal to 0.35 over 0.15 times 0.3 squared. Don't forget to square it because H2 is squared, so your H2 value needs to be squared. And I get that K is 25.9. or 26, depending on how many sig figs the question asks. From the initial values, you would use 3 sig figs, but that last value has only 2, so it just depends. Also remember, K has no units. All right, and again, if you have questions or need extra practice, I have plenty that I can get you. Okay, so this walks us through it. I'm going to do another one. Okay, so this is the same situation. It's the same equation, but it's got different initial values and it tells us a different equilibrium concentration. So again, we do our ICE. I've got CO plus 2H2. You should always write your equation at the top. Occasionally on here, I will not, just for space, but when you have this space, you absolutely should. Okay, so I've got 0.27 for carbon monoxide, 0.49 for hydrogen, no methanol. Again, we're proceeding in the forward reaction, so this is plus X, minus X. Again, the minus 2X is because there is a 2 in front of hydrogen. And it tells me the methanol concentration this time is 0.11. This is 0.27 minus X, 0.49 minus 2X. Okay, this actually makes it easier because it's basically telling us X, because 0 plus X is 0.11. Okay. So I've got 0.16 here and 0.27 here. Once I've got that, I'm going to plug it in to my expression. So 0.11 goes on top, 0.16 times 0.27 squared. And this one comes out to 9.4. We're just going to leave it at that for the equilibrium expression. Again, if you have questions, please let me know. All right. Now we're going to talk about our reaction quotient. This is something where our equilibrium expression is not in equilibrium. That's why it's called a reaction quotient. This uses initial values. Okay, the way you write Q is the same as K, but instead of equilibrium values, we're using initial values. Okay, so here's our example. Q looks just like K did. Sorry, y'all. And our only difference is that we're using those initial values. Okay, this is going to be very important because sometimes you need to relate Q to K, and this is also going to reappear once we get to chapter 17. Okay, so you need to make sure you've got this down. This is somewhere in the 30s for the slides. Okay, so if Q is greater than K, the products decrease and the reactants will increase. If you want to write it the other way, K is less than Q, that means the reaction goes that way. Q is greater, so all I'm doing is flipping these so the arrows match up. And then when they're equal, we're at equilibrium, nothing changes. Okay, this is just showing you, according to equilibrium, what way we'll go. All right, so here we've got, it gave us Kp, it gave us pressure values, and then that's what it contains originally. Is it at equilibrium? So first we need to do Q. You always write the equilibrium expression. Okay, so I've got 0.355 squared with 0.114 at the bottom times 0.102 at the bottom. Okay, so we're going to calculate and I get 10.83. Okay, so I'm going to write it okay, we know that Q is less than K because 10.83 is less than 81.9. So if we write it the other way, that's the easier way for me to remember it. What way will the reaction proceed towards the products? All I did was flip it, okay? You can do the same thing with KC. I'm not going to work that one. These really aren't that hard because all you're doing is plugging in the numbers. You don't have to do an ICE table. As long as you have which direction they go, you'll be fine. Okay. So they're going to tell us we need to use the ICE tables now. Really, you need to compare Q to K, but most of the time you don't have to do that. Okay, they're going to use the quadratic equation sometimes. We are never going to use the quadratic equation because I know y'all can do math, and I don't really care if you know the quadratic equation. That's not what chemistry is about. I need to know that you know the chemistry behind it. So we're always going to use this approximation method, okay? So again, we set up our ICE table, do initial change concentration. It's showing you what you do with them. One needs to be subtracted for X, one needs to be added. All right, find the equilibrium concentration of those given this initial value. Okay, so this is a little different. Okay, remember we should always write our K NO2 squared over N2O4. All right, so once we do that, we do ICE. They gave us only the initial value for NO2. They didn't give us anything here. So this is plus X, and we've got minus 2X. Remember, it cannot proceed from 0. Otherwise, it won't make anything. So yes, we should have found Q, but we don't have to in a situation like this because the only way it can go is backwards. All right, so this is 0.1 minus 2X, and this is just X. At this point, so this is a little different. This time it gave me K. So I've got 0.36 is equal to 0.1 minus 2X squared over X. Okay, so that is a perfect square. So for this one, we're not going to approximate. Now, normally we will approximate. So this comes out to 0.36 X is equal to, actually, let's just go ahead and approximate. So for approximations, we get rid of plus and minus X, however many of them there are. So this just is 0.1 squared, which is 0.01. And I get that X is 0.02778 molar. Now, so this is the concentration of N2O4. So it wanted that, but it also wanted the concentration of NO2, which is 0.1 minus that, minus 2 of them. So this is equal to 0.0444. Okay, don't forget that X is a concentration most of the time, especially if you have these brackets. Okay, if you look at this PowerPoint, it's going to show you the way not to do the approximation, but again, we're going to do the approximation the whole time. Okay, so there's no reason to do it any other way. So here, like I said, they show you the perfect square. They do plus or minus. X is a little different. It's slightly smaller, but not too much. Okay. I'm not going to do the next one because we're going to run into the same issue where it's not going to come out nicely. Let's do a different one. Okay, so I've got I2 plus CL2 yields to ICL. We did already do this one. And remember for pressures, it's really, you don't use brackets. I mean, here's the deal. I'm not going to see them, and this doesn't really carry over too much to organic, but if you're going to need to take chemistry higher than organic, it's going to be super important. So just make sure that you're aware of that. I took analytical chemistry, and it is a whole class basically over Chem 2, but it dives way deeper than before. Okay, so we do our ICE table. Again, now we're dealing with pressures. So I've got 0.1 atmospheres, 0.1 atmospheres, and 0.1 atmospheres. Find our equilibrium. Okay, this time we do need to use Q because otherwise I don't know what direction we're going. And look, Q happens to be 1, y'all. That means, well, that was easy math. Okay, so Q is less than, okay? So it's going to proceed in the forward direction. Okay, so this is going to be plus X over here on the reactants, or sorry, the product side. And you're going to have minus X on the product side. Plus X on the products, minus X on the reactants. So I set it up. 81.9 is equal to, again, 0.1 plus 2x squared, 0.1 minus x, and then 0.1 minus x. Okay, this one's a little different just because if I cancel out my x's now, everything goes away. So we are going to go ahead and look at what they do. They solve for Q, just like I said. Proceed to the right. They do the x's. Okay, so here, look. They notice, by the way, it's a perfect square. Again, you will not have to deal with any of this. And after they do all this quadratic math, which you don't have to do, they come out with their x value. Remember, x is not the answer. It asked for the partial pressures of I2, CL2, and ICL. So it's going to be 0.1 minus that, and 0.1 minus that. Okay, so I got 0.027 atmospheres, 0.027 atmospheres, and then 0.1 plus 2 of those is 0.246 atmospheres. And that's just a checking for your understanding. All right, here's the approximation, and this is what we are going to do. If X is less than 5% of the initial concentration, then you can use the approximation method where you don't have to do the quadratic, which is what we're doing, okay? So they gave us Kc, they gave us an equation, and they gave me initial values. However, notice the initial value of this is not a molarity, but our ICE table has molarities in it. So we're going to have to convert that. All right, so I've got 0.0125 divided by 0.5. So my initial concentration is 0.25 molar for H2S. Okay, and they didn't give me anything over here. So this is minus 2x. plus 2x. Sorry, y'all, my allergies. Sometimes when I drink coffee that's got a lot of dairy in it, it makes me cough more than normal. All right, so this is what we're looking at from our ICE table. I need to plug stuff in. I've got 2x, and that's squared, times x over 0.25 minus 2x squared. So remember, this is the approximation method, which says we get rid of all plus x and minus x. So this disappears. So okay. So when I do my 2x squared, I get 4x squared times x is 4x cubed. When I solve that, I get x is 0.00138 molar. Okay, remember, that's not what it asked me. This is the concentration of S2, not of H2. H2 is 2 of those. Okay, also don't forget your units when you're doing concentration. If it asks for concentration, it's molarity. If it asks for pressure, in this chapter, it's going to be atmospheres. Okay, so just make sure you know what it's asking for. I'm a 0 off, y'all. It must have been a typo in the calculator. It'll tell you in Mastering Chemistry what's going on. I'm not using a calculator where I can scroll up enough to see. Okay, I'm gonna go through another one. It's the same process. And this is where we're stopping today. Y'all have a good day.